Okay, let's get started. So we have talked about buffer overflow, especially how to overflow the return address. In some cases, you cannot overflow the return address directly. You can overflow the saved EBP, actually change the return address of the upper layer function. So today we will first look at some real-world examples, why they are still relevant today, because some of the techniques we talk about they were developed in the 80s, 90s. Today. Then we will talk about address space layout randomization and also a lot of defense today. So today, the class could be a little bit shorter than usual. Then next 2 weeks, we will be having a share code workshop. Then we will work on our own share code, try to make them more complicated or smaller to but still you will be able to capture the flag. So the first real world example I want to show you guys is the Morris wall. We talked about that at the beginning of the buffer overflow module. Bug, or this is an exploit that made buffer overflow world famous or infamous. And now you look at the code, and put you back to the 80s, you will be able to exploit something like this, right? So this is a vulnerability in the finger daemon. So daemon is basically a server or service in Linux or Unix systems. Windows call it just a server, I believe, service. Yeah, in Linux we call it a daemon. So this finger daemon, that's why the program usually is called finger. Other Linux programs end with a D. This means that it's a service, that's a daemon. This program will just tell a remote user who has been logged in to this local machine, who has been running programs here. Okay, to a finger who is using this computer. The program is actually, at the beginning, it's simple like this. There is a main program, and of course, the C code here look also slightly different from our modern C, right? So you can see there is argc, argv, and there is another declaration. What is the type of argv? So the syntax is a little bit different from the modern C, but you can still understand what it is. So here, that's a char, that's a pointer, but this can be stored in a register, so that is a keyword. I think modern compiler also still have this register keyword as a keyword. To tell the compiler you should use register to store that instead of using stamp to store that. So that is also a register will use that. Then there's a buffer, there's a 512 bytes. Then if you have been doing socket programming, everything after this should be quite familiar with you. This is just a socket address. Then there's a process ID, there's a file pointer, there's another array of pointers. The problem is this line, it uses gets, and it puts the input from the network. So gets take input from standard input, std. So on our server, every program, their standard input is the terminal. That's why it is getting your input from the terminal when you type. For this program, obviously, the std in is not the terminal. It is from the network. It's probably forwarded from the network eventually to std. So gets will store whatever from the internet to this local variable line, which is big, 500 bytes. But obviously, the input can be much, much bigger than that. Then we can have a buffer overflow. And this is the very first famous worm that as a bug. And the worm developed to targeting this, and actually several other programs, not only this program. So Morris developed exploit and also find bugs in multiple services, not only FingerD. So the exploit or the worm he developed will get a shell and will also duplicate itself, try to send messages to other machines on the internet. I believe at that time, 60% or at least 50% of the machines on the internet were compromised because of this. And this is way before the defense we looked at, right? Stack Canary. We have talked about Stack Canary. We talked about what did we talk about? Shadow Stack, right? So those were developed in the late 90s, early 2000. So this is way before that. It took the world another 15 years after this to come up with something like Stack Canary. So this is one example. This is in 2000, another buffer overflow, but this buffer overflow is not as straightforward as the previous one or as the one we saw in the class. So here we have a local variable, char n-pads, which has a fixed size, obviously, and the size here is 1024 bytes. That's the size of this buffer. A for loop. If you only look at here, you don't really realize there is a bug. So I start from 0, then I is smaller than the size of the pads, which is 1024, and the size of that minus 1. Okay, so looks like a same code. Here we have an I++ here. The problem is there is another ++I for this condition. So if there is a double quote character, there could be a ++I, which will make i's value go beyond 1024. But it can actually go beyond 1 byte. Okay, only 1 byte. So if you send data which is 1025 bytes and with a special double quote character there, you can trigger this branch and eventually overwrite the buffer. Okay, the buffer is 1024 bytes. You can overwrite 1 byte. That's it. Okay? So by overwriting that 1 byte, obviously you will not be able to overwrite the return address because before that you still have saved the EBP. Right? But even that 1 byte may be enough to do some damage. First of all, at least you can do a DOS attack. You can crash the program, right? And maybe you can even, depending on other situations, maybe you will be able to take control of the system. Here's an example. This is off by 1 byte example. Here we have a more recent example of an EV charger. So I think this was discovered years ago, and now there are a lot of activities. Many companies, they have this kind of competitions, especially Linux kernel have those kind of competitions as well. If you identify a bug, they fly you to a competition and you show them a working exploit, and they will pay you for that. You get some bounty money for that. So this is also from a Palm2O event, and this is specifically for the automobiles. As long as you have something related to cars, like this one, the EV charger, that is part of that ecosystem, you can show them there. So this vulnerability is on, first of all, it's on a different architecture. This is not on x86, but it's about x86. This is on a different architecture. Sometimes a different architecture make hacking easier. Sometimes makes it a little bit harder. First of all, totally different instruction set. The instructions you learn in this class, they are not showing up for different architectures. MIPS, there are many small companies for, especially in the car industry, the ECU, electric control unit, they have different microcontrollers. And there are some big players there. They do not use ARM or Intel architecture. And also RISC-V is a popular one, getting more popular in recent years. So on those architectures, especially for microcontrollers, they are not microprocessors we use on your phones, on your tablet, on your laptop or servers. Those are microprocessors. So those CPUs has a memory management unit. You can do memory virtualization there. You can do all kinds of access control on different memory regions there. But for microcontrollers, their CPUs is much simpler. Usually, they do not come with an MMU, so you do not even have memory virtualization, right? Which means what we're going to talk about today, address space layout randomization, would be difficult to implement there. Still possible, difficult, and also much more expensive to implement there. Then, they do not necessarily have all the other features at the hardware level as well. So they do not necessarily implement the software security features we talked about, like shadow stack, like even stack cookies, or even if they implement stack cookie there, it may not work. We actually have a paper published 2 years ago talking about for those microcontrollers, the stack cookie mechanism is not really working. A lot of those microcontrollers, they boot, then they stay there for 10 years. And we said the stack cookie will never be regenerated. So as long as it is disclosed once, even though the boots, it will randomize that, but as long as it's disclosed once, then forever you will be able to hack the system. So in this case, this is a source code there. So this is also not the bug here is not that straightforward. So what they're doing is this program here is trying to replace or expand some kind of format, a little bit like a format string. Okay, so if you have been using printf, sprintf, those kind of functions, you know the first parameter of that is a format string. Actually, format string, we will talk about that again in the second half of the class. There is a class of attack for the format string vulnerability. So here it's not like that. We're not talking about standard, the C library format string. They have their own format. They're trying to expand a format string to a longer one. Okay. So we say we have a buffer here, formatted message buffer, 192 bytes. Before that, we have another scratch buffer. Then there are some format strings. At then T here basically means this should be expanded to the current timestamp. That's it. Okay. And they allow you to have 15 those kind of format. Let's see what I call this. Just maybe just tags. Add T, that's a tag. Each of this in this string, if this is a string, this is only 2 bytes, right? Only 2 bytes. But this one will be expanded to the timestamp, which will be 23 bytes. So 15 of this will be more than 345 bytes. It's 192 bytes, even though there is a lot of scratch together, it's not this big. So on this architecture, they were able to inject a lot of these tags to overflow the buffer. So of course, they're trying to override the save the PC here. It's not save the EIP because or RIP because this is not x86. But you can say the idea here is the same. You override the return address. You somehow have your own malicious code. Not necessarily return you a shell, but something malicious. Then you take full control of this system. This is a second example. There are, like I said, there are many challenges like this. there are a lot of bug hunting programs out there as well. They are slightly different. The bug hunting programs usually are only looking for bugs. As long as you can prove that they have a bug, your proof of the bug is not necessarily an exploit, which means you don't have to exploit that. Maybe you crash the program, that also counts. Then there are hunt-to-own activities where you need to show that you not only can crash the program, you can take full control of the system. So you need to have a working exploit as well. So this is a screenshot I took from automobile hack competition, and the leading team took almost 300K home for that competition. And this is 2024. Things are changing rapidly, evolving rapidly recently because of large language model, AI, agents. So many people are developing automatic tools, and hopefully those tools can participate in those kind of competitions. We also have a team doing that. We just started. We want to build an automatic agent to compete in those CTFs and also those kind of activities. So if any of you are interested in that, talk to me. Maybe you can also contribute there. Okay. So then what are in this class, I teach you how to read the source code, read the binary code, and find the vulnerabilities and manually exploit them. You can use tools like POM tools, but still, you need to understand every byte of it, right? Well, sometimes even every bit of it. You need to understand everything. The problem is it's not scalable, right? You spend one day, several hours, finish your homework, only 5 challenges. It's not scalable. There are billions of software projects out there. We need to find bugs. How can we develop automatic tools to do that, to make things faster? I don't cover that in this class. I do have another one, advanced software security class, where we cover that. I do not offer that every year, because I haven't accumulated enough population for that class, right? Because this class is a required prerequisite for that class. Before you guys learn how to manually hack things, I don't think you should directly jump to that. But I want to give you a little bit sense how you can do that. There are many approaches. First of all, you can do static analysis. Static analysis basically means you do not run the program. You look at the source code, you look at the binary code, like what you guys are doing. What you guys doing for hacking are both static and binary, and dynamic. Then, static analysis tools obviously use program analysis techniques. And the program analysis techniques is very related to compiler. That's why a lot of things were done as a compiler front end or back end. There are many tools. Wind is one of them. It's computationally expensive. It's very slow, but it can find many kind of bugs. Then in recent years, another area is called sanitizing. They are simple instrumentations to change the code a little bit here and there. So then they are used with fuzzing, a dynamic analysis tool, to feed different input to the program to make the program malfunction or crash. But sometimes, even if the program malfunction, it will not manifest the problem. Think about the very first hack we did in this class. There was a local variable called authenticated or admin or whatever. It's a local variable. Then after that, there's a buffer. We're trying to override that local variable, right? We didn't try to override the return address. Okay? But by override that sensitive local variable, we get a privilege escalation there. Okay? for those kind of bugs, it's not going to manifest itself. It doesn't crash the program. Still override, but it doesn't manifest itself, right? So the job of a sanitizer is to make sure that those kind of a program, those kind of input will manifest as a detectable behavior, such as crashing itself. The idea is very simple. We have, let's say, previously we have that admin variable here, buffer here. The override is from buffer to admin. So the overwriting behavior itself will not trigger any bug, will not trigger any crash. So what the compiler can do is, between each variable, we are going to have some red zone or something like clear. Right? Then between each variable. So even if your buffer override from buffer, you override admin, you have to override the red zone because it's a sequential override. Then later we can detect, oh, the red zone data is overwritten, so we can detect that. Or, well, there are other smarter approaches to make this manifest even faster. Right? So those are sanitizers' job. So there are all kinds of sanitizers to find those kind of buffer overflow, find undefined behaviors, and many other approaches as well. There is also another tool developed by GitHub called QL. This tool, they will read the source code and analyze it and put everything in a database. Then you can just query this using their own query language. For example, the query language could be they don't have an example here. For example, find dangerous buffer overflow functions, something like that. Another direction is formal methods. You can formally prove or reason the properties of programs. There is a tool called, right now they call it ROC now. The problem of that is formal verification usually is also very expensive, especially when the program gets very big. Formal verification may not able to return quickly, or in some cases, they cannot even return. Dynamic analysis-wise, fuzzing is still the most effective approach. In our lab, we also do fuzzing, especially for embedded systems. Fuzzing, the idea of fuzzing is very simple. We just feed the program with just some random input and say how it behaves. If it crashes, it means there's a bug. If it's not C code, if it's Java code, technically you don't really have the classic C memory corruption problems, right? There's a Java virtual machine, but still the program could crash. The program could throw an exception. So there are still detectable behaviors for malfunction. So for fuzzing, usually we go for coverage-based, which means we want to cover different basic blocks. We want to find some input that can trigger new basic blocks or the transition from a basic block to another basic block. Then from those inputs, we generate more input and eventually find bugs. There are also symbolic execution or concolic execution for you to run a program without using concrete input. So far, when we run programs, we are using a concrete input. The input is a string. The input is a value. That's a concrete input, which means when there is a predicate, the program will just take one branch, right? Because we have a concrete input, the programmer decide which branch to take depending on the input. The idea of symbolic execution is we want to concurrently execute this program at different branches using a symbol instead of using a concrete input. Then later, we can collect all the symbols, the expressions of the symbols. Then we use some solvers, like math solvers, to figure out the concrete input that can trigger different branches. So they were used with fuzzing to try to achieve a better coverage. The problem with that is also very slow. That's why now many people, including us, we're looking at using large language model to generate input for better coverage instead of using symbolic execution. Rehosting is another idea for all the bugs you guys have been cracking right now. It's x86. We have an environment. But imagine you want to hack this projector or hack that TV. They have bugs too. They have CPUs. They have multiple CPUs. They have bugs. But how do you find the vulnerability there? Right? You can give input to that device, or you can dump the firmware of that device and try to emulate them a server, a powerful machine, where you can fuzz at a much faster rate because you can run, because that device is not as powerful as even our virtual machine. AI and large language model will play in the future. To know more about fuzzing, there is a book I recommend you guys to read. That one is not specific to C programming language, but the idea is the same. Okay. That is basically what I want to talk about, some real-world examples. Then any questions? We're good? Okay. Okay, then we have two more differences to talk about today. We already talked about non-executable stack. We know how to bypass that? Oh, we don't know yet. We know return to libc, but we don't know the general version return-oriented programming yet. We talked about stack calorie or stack cookie. We can bypass them if the program is a forked program. We talked about shadow stack, which is not necessarily deployed everywhere so far. So today we will talk about two more techniques. One is called ASLR. Another one is called Seccomp. So ASLR is already deployed everywhere, not necessarily on those IoT devices, but on your laptop, tablet, phones, desktop. Those systems all have ASLR. We have been disabling ASLR for this class on our server, and today we enabled it for this session. So after this class, we are going to disable that again, so you can finish the homework of this week. But we are going to show you that it's still bypassable. Another technique we'll talk about is Seccomp. That's basically like a firewall. It's not a firewall at the network adapter or network layer. So usually when you think about firewall, you're talking about a network firewall. You have input from the internet. You analyze the input, you analyze the network packets, looking at its TCP headers, UDP headers, IP headers, whatever. Then you decide to block them, right? The same idea, but at the system level. Make system calls. The OS will decide if I allow this program system call. Even more complicated than that, what kind of parameters we allow the program to make this system call. Okay. So ASLR first. ASLR is short for Address Space Layout Randomization. A little bit history of this. started as a Linux patch in 2001. Then OpenBSD picked it up 2003. Then Linux formally started supporting that at version 2.6 for user space ASLR. Okay, so in this class, we're mainly talking about the user space ASLR. Then Windows Vista 2007 for user space as well. After that, iOS, Android, then Mac OS deployed the first kernel space ASLR in 2012. So the user space ASLR at a very high level, how it works is when you launch a new program, the E-system call, right? Not fork. Same as stack cookie. Fork doesn't really change things. EXE when you launch a new program, the address space of that new program will be randomized. Okay. So far, all the programming I'm saying, the code is placed at the same virtual address. Okay. Not a physical address, virtual address, same physical virtual address. The libraries, they are placed at the same virtual address. So with ASLR, those addresses will change. Then the kernel space ASLR happens when your system boots. Okay? So if you never reboot your system, it's not going to randomize things. Whenever a program is created, it will randomize that. So if your program runs forever, then it still cannot get randomized. That's the current implementation. Of course, there have been some academic prototype to make it much more frequent, but they're not necessarily deployed in real world. How do you randomize the address space of a program? It's actually a very simple thing, especially for some of you who took the computing system class, right? I showed you code to load an ELF file, and the loader in the kernel will decide which address you are going to load this image. That's it. So when you load that, you just add some randomness. That's it. Very simple. Okay. That's it. But you can do that easily because you have MMU, because you have virtual address. You already have the hardware layer support for that. If you do not have MMU for microcontroller-based systems, some low-end IoT embedded systems, implement this would be a little bit more challenging. Especially a lot of IoT devices, the code is in Flash. The code is not really in memory, in DRAM. The code is in Flash and directly executes there. So it's fixed address. So if you want to randomize that, you first need to move them to memory that execute at memory. There are papers talking about that as well. Okay. So why this is helpful and what kind of attack it can defeat? First of all, we have learned that how to inject the shellcode. And to inject shellcode, we can attach a very long knob select at the beginning of your shellcode. Remember that, right? That can be big. That can be several kilobytes or even megabytes. So even if you randomize things, you still have a very high chance to hit somewhere to the knob select. So for that case, it's not really very helpful, this defense. However, think about attacks like return to libc or return to any other function in the address space. What you need is overwrite a return address on stack, and the content you need to write there is the address of that say library function, right? And that is an accurate, precise address. You cannot put an offset there because that's existing code, right? Or for return-oriented programming, we will study in the second half of the class, the same thing. You are looking for gadgets. Those gadgets are very small. 10 bytes, 5 bytes, 2 instructions, 4 instructions. Okay? And you have to know exactly where they are. For those things, if we just randomize their address, every time this program boots, they are at a different address, different place. The attackers, it's difficult for them to know where they are and difficult for them to jump to those or return to those addresses, right? So when ASLR is enabled on Linux, there are many parts we can randomize. The first is the executable itself. As a software developer, you develop the main part of the program. You use other libraries like libc. Libc is not necessarily of your L file, your executable. Your executable itself has to be compiled in a specific way, which we call position independent executable, PIE or PIC, position independent code, which means this piece of code can execute no matter where you put in the address space. Okay. This probably is not that straightforward because obviously you were saying why my program will not execute at other place. If you are just talking about one instruction, obviously you can put it in any space. But that instruction will resort to resources at other memory locations, right? It will use a string. If you do a printf, there is a hard-coded string. That's the address of that string. Hard-coded, probably hard-coded as a parameter of that printf. If you move that to a different, move this piece of code to another place, you probably also move that string to a different place, then your code has to be changed somehow, right? So we need to compile the code as PIE code. Global offset table actually is part of that, so they can also be randomized. Then heap or stack, they are not really part of executable. They can be randomized as well. We'll also do that. Shared libraries, they can be randomized. mmap, memory mapped areas, also some libraries, they are brought into memories through the mmap interface, not necessarily through other interface. They can also be randomized. Also some old approaches for system calls. So in our server, we actually use this approach to disable and enable ASLR. Linux provides us with an interface, the proc. So proc is a pseudo file system. It's not really some file on your hard drive. It's just a pseudo file system, and it hosts an interface called randomized _ virtual address space. So that is kind of allowed for us to turn on or turn off ASLR. Of course, you need to be a root for this one. So far in this class, we set that as 0 to disable ASLR. And if we set that as 1 or 2, it will enable ASLR. This knob eventually maps to this kernel variable to define whether in this kernel file to define whether we want to have ASLR. And this is user space ASLR. And this is just one code snippet in the Linux kernel to implement the ASLR. And this is only for the executable or L file part. Like I said, there is also heap part, stack part, memory map part, right? It's not showing here. So here, as you can see that the Linux kernel will load programs to an address, and this address, load _ BIOS. Okay. So that is basically the base address to load your L file to. Okay. There is a hard-coded base address. Then if your program is compiled with PIE, and also in the system right now, we enable ASLR. We'll generate a random number here by calling this function, arc amap random number. That's it. Okay. This function will just return a random number. That's it. That random number, of course, has a range, will be added to the hard-coded base. Okay, as simple as that. Just the 2-3 lines of code in the kernel, you implemented ASLR. Of course, because we already have the other hardware support there. A little bit more on this PIE. Like I said, it makes sure that the piece of code can run anywhere. Doesn't really matter. Doesn't need to be hard coded. We use 2 simple examples to show this. So, simple program, star PIE and ASLR no PIE, the same program. Okay. Main function. The main function for toPrintf, it shows the main function's address. That's it. That's a function. And we're going to compile this, use 2 different options. One with PIE, one without PIE. So let's take a look. We don't have this. A single module. Starting with module. Okay, so the TA has already enabled ASLR on this server. The program we have is ASLR module. It prints out address of different modules of this process. What are the modules? Where the code is, where the read-only data is, where the data section is, where the tables are, where the stack is, where the heap is. So I run this program twice, as you can see here. And the .text section and other .alt sections, they have different address. Notice that? Other displays of 0x, we should fix that, but you get the idea here. So the first time we run the program, the text section is at 5657 C1B0, right? Second time we run it is at 659 A1B0. So it's different from the first time. Same program, we run it twice. The data section and other sections, the same, the address will change. But we also compute the distance from other sections to the .text section. So if the offset is positive, means that section is at a higher address. If that is negative, means at a lower address. As you can see here, the .data section, .bss, GOT, PLT, interpreter, dynamic symbols, read-only data, all of those, even though their address change, the offset to .text is always the same. You see? That's fixed. Okay? Why is that?
based on the global offset table, right?
So actually, I already showed you code why in that case, because all those sections they belong to the L file, right? And when the L file is loaded, in the previous example I showed you, the code, Linux kernel code showed you, the kernel load all of them as one big piece to the memory. So those sections, even though they are different sections, they are one big piece loaded to the kernel. So they will have the same offset. Okay. And the code itself will rely on that as well. So they have the same offset. Or if you look at the stack or heap, they are at different address as well. Stack, this one is at 800. Stack here is at 8700. Stack goes down, heap goes up. But their offset is also different. The first one, the offset is 512, but this one is 100. Okay. That's because the stack and heap, they are not part of the L file. The source code I showed you is just for the L file part. I didn't show you the source code for stack and heap. There are also randomness there, and it's just an independent randomness. Yeah.
Will environment variables also change where they are?
Yes, because they are on stack. Yeah. For modules. It's still 4-bit, the same thing. The address changed. And you get more randomness here. So previously, you have like 3 digits different, right? 3 digits is like maybe 12 bits. So here we have how many digits different? Starting from here to 5 digits. So the randomness we are getting here is 20 bits. Much more secure. But the stack and heap, you can say the offset different. But this one different. So that's for modules. If we go to let's say modules without PIE. This is from the same code. We just compile it with no PIE. And we're still running on the same Linux, which ASLR is enabled. Because ASLR is enabled, the kernel will try to randomize the address space, but the kernel realizes the program doesn't support that. So the OS has to load the program same address. So you can say we run it twice, and all the addresses they are the same. Because we didn't compile this as PIE program. If the OS loaded it to another place, the program may not be able to run. It will crash. The symbol level, I go to the symbol level. So this is another program at the symbol level. We print out the libc function's address, where it's printf, where it's memory copy, also out the module function's address. Then we have global variables. Let's have 2 terminals to compare better. So now we can compare. We run this program twice. Leave sys address, you can say everything is different. Printf, memory copy different. But the distance between printf and memory copy is fixed, the same, right? Because they belong to the same library. When the OS loads the library, it just holds that big piece there. The address of another function system is there, and the distance between printf and system is also the same, EB30. And the module function, which are the functions in your executable, they also have different address. Main, add, subtract, compute have different address. However, the distance between main and the compute is the same, 44, because they belong to L file. However, the distance between main and printf, they are different. Left-hand side, we have FFD. We have C2 FFD. Right-hand side, we have 03 FFD. See? That's because they belong to two different modules. One is the C library, one is the L file. They are loaded at a different stage. Okay. They are not randomized at the same time. The random value you get is different. Then we have global variables. The global variable obviously is part of L file. So the distance between main stays the same. 2D5B stays the same. See? Then the distance between the global variable. Now the global variable and memory copy, that will change because different modules. Then uninitialized variables, the same thing, they're part of the L file. However, local variables, they will go to the stack, right? That also changed. So that's ASLR. Okay, so go back to this example, this very simple program. If we compile this, if we look at the disassembly, we will notice something different. The main function for the no PIE part, the program is short. We have NBR, we have some instructions at the beginning. In the homework, you have a hard version of a challenge to solve last week, right? So you'll have seen something like this at the beginning. After that, you have that basically to align the stack of the main function. Then, when we try to call a function, this is something we're familiar with in the last several weeks of that function. Not necessarily directly that function, but it should be an entry in that global offset table for that function, right? Remember that. And that is a hard-coded address here. You can see here, hard-coded. Hard-coded in the instruction. And also, this one will print out the string, which is hello world, whatever. The string is a read-only data. You're not supposed to change that string, right? So that data goes to .ro data section. It is still part of L file. So it still has a hard-coded address. That's why here, the push, we're pushing a hard-coded value. That's the address of that string. Same thing for the second printf as well. Then the PIE version is different. It's different because, so let's say, we still have puts here. Then we still have puts here. You can say, first of all, you notice this part. This address, which is a string's address. Previously, the string address is hard-coded. Now string's address is EBP minus a fixed number. See that? And where do we get the value of EBP? EBP gets its value from a function call for the underscore x86 dot pcsync dot bx. EBX, not EBP, sorry. So this function will put the current address of this instruction, of the call instruction, or next instruction actually in this case, but same idea. Address to the register BX or EBX. It is trying to find out where it is. This piece of code is trying to figure out its runtime address. You get what I'm saying? Okay. Because it is randomized. It doesn't know at runtime where it is. OS randomized that, right? So it's trying to find out at runtime where it is. And we have the code, we have all the other data, and they have the fixed offset. Okay? So with that fixed offset, they will know the runtime address of that string. Does that make sense? That's why they first get the current address to this register, then they add a fixed offset here to EBX. After that, then another fixed offset will tell us where the string is. Maybe this offset is for a different landmark, whatever. So a little bit more about that. You have seen this function multiple times when you saw our code, because some of our programs, we compare them with PIE, that's why. You do not necessarily say this version, .ax. You may say other versions, .ax, .cx, whatever. Those functions, they are not part of a C library function. They are just inserts there by the compiler. It's very simple function. It could be as simple as this, just 2 instructions. That's it. Okay, but that's a function. That function will just return the current address of that instruction or next instruction to the register you specify, BX or CX or whatever. Okay. Why do we need a function for this? The 32-bit instruction set doesn't provide you an instruction to get the value of EIP. There is no instruction move EIP to EBX. That instruction doesn't exist. Okay. So that instruction doesn't exist, but how can we get the value? Write this function. Okay. This function doesn't even have all the complicated prolog, epilogue of push EBP, move ESP to EBP. We don't even have that. We have only 2 instructions. The first instruction is move whatever ESP points to EBP, then return. That's it. So why this works? You have to call into this function, right? When you call into this function, what happens? What does call instruction do? We push the next instruction's address to the stack, right? Then we move the target address to EIP, right? So after this call instruction, there will be just a regular instruction in that function. And that address will be pushed onto stack. Then we are here. So ESP points to the return address, which is the next instruction after call. We move that address to EBP. After that, we're done. We just return to that instruction. So by doing this, we get the EIP's value, or technically EIP plus 4, right? But whatever. So even though we don't have an instruction to directly do that, this is a small trick we use. We probably will also use tricks like this when you develop shellcode. The 64-bit version is much easier because the 64-bit of Intel x86 allows you to directly use RIP-based addressing. There is a new instruction here. Load effective address RID brackets RIP plus a fixed number. Okay. So RIP is basically this value, right? At runtime, this value. Then fixed offset, so we can get the strings address. That's it. So this doesn't exist in 32-bit version. So last semester when I was teaching computing systems, one of the assignment was to develop a calculator, right, using 64-bit assembly. But in the class, we didn't teach you guys to use RIP-based addressing. We want you to hard code that part. Then there are many students, they write perfect assembly code with RIP addressing. So it's easy for us to detect who is using large language models. Yeah. The 64-bit without PIE, you can see the same. This is hard-coded address. Yeah. It's for 64-bit. So that is a module thing I already showed you. We can skip that. Symbol, this is a source code for that. We already see the results of that. We have an add function, sub function, compute function. Then we just print out the address. And you saw the differences there. Also, if we use other tools like NF, readelf can also do this. You can find all the symbols. If this is not a PIE program, let's try that. A long PIE program. This is a long PIE program. The first column is the address of it. The second column is the type of it. The third column is just the name of that symbol. Let's see. What do you notice here? Especially the address part. What do you notice? It's 08049 something. That's the functions, right? That's the sections. So this some of the functions. Underscore started a function. Stack check failure, that's also a function. So even those functions, they have the function, but still, the address, they look like real address at runtime, right? 8 something real address at runtime. So if we debug this program, we just let's say we just run this program. The breakpoint on main. Now we are in main, then we just do a disassemble. And you can see those addresses. Those are the same addresses as we saw when we use a static analysis tool like NA, which we do not run the program. Which means when you use a static analysis tool, you are getting the runtime address. Okay? So those addresses are already written in the L file. And the OS, to load that program, will load those modules at those addresses. Okay? No randomization. But the same version of code compares. Did we do module or? PIE. We do an M again. Same symbols. Look at those addresses. What do you notice? Those addresses are bigger or smaller? They're smaller. Why they are smaller? Are they the runtime address? Do we even know the runtime address? We don't. Only runtime will know the runtime address because there will be randomness. Or because those are the offsets. Okay, they are the offsets to the beginning of the module, not really the runtime address. That's why they are much, much smaller. So the overhead of this for 64-bit, it's basically just one instruction like this, and one more instruction. So the overhead is very small. Sometimes it can even be free, because with the optimization and microarchitecture level, this can even be free. For 32-bit, it's a little bit more expensive because we do have a function call. We have a function call, we execute one instruction, then we return. So 3 instructions technically. So some reports say that's almost 3%. So how do we bypass this? There are many ways to bypass this. First of all, you can see the granularity is not perfect. We divided this into one process. We divided this into several huge modules. The L file itself, stack, heap, library. Randomize those. We're not randomizing inside each module. Okay, that's the current implementation. Scientifically, it's possible. It will be more complicated, higher overhead, but it's possible. I'm just talking about current implementation. We're only doing that. Granularity is not free. If you have one leakage somewhere, then you basically is able to hack that module. There are only like 5-6 modules there. Okay. For the L file, if there's one bug to show you where one function is, says you can know this function's offset to the whole part. Then you can also know the offset of that function to every of other functions. Then you basically get the address of everything. There are many different levels of vulnerability as well. Like even the micro architecture level, side channels can disclose some information to bypass that. So our job is to bypass several of this. Now ASLR is enabled, but still going to get the flag. So this is our first challenge here. We have main function called valfoo. Valfoo print out its address. Then there is a buffer, 8 bytes. It takes some input from you, then just returns. That's it. How do we? So before we have ASLR, how do we hack this one? There's no stack cookie. There is no. I don't remember if we have non-executable stack. This one we don't need an executable stack anyway. So let's assume we have non-executable stack, but no stack. Hack this one. Yes, we just overwrite the return address for valfoo's frame stack and return to either print the secret or print the flag. Either way is fine, right? The problem here is you need the address of print secret and print flag, but you don't know the address. Previously, you know the address. You use GDB to debug that, to figure out, or you do static analysis. Here, you don't know the address anymore. But we're giving you some hint. We're telling you where a valfoo is. Okay? So, how can we use that information? Exactly. Because they are supposed to be at the same module, right? Both of them are in executable. Even that print flag is actually also in the executable. So how I implement that is I implement a header file, a save file, then we compile with this one. So eventually it goes to the same L file. So to solve this, let's take a look. Space 1. 64-bit will be the same actually. First of all, this is the disassembly of waffle. You can say it's trying to get a relative address, get the runtime address using the getPC function. Then call printf. Printf is getting first address from bx minus something. Right? That's it. So if we run this program, it's us this address. Waffle is here. If we run this again, it's different. So previously is 5A8. This time is 5. So only 2 digits changed. Problem, I think it's a little bit more than that. Yeah, digits. So the randomness here is only 8 bits. Brute force will only take you 256 times. Right? 8 bits of randomness, not much. Okay, so for an M, Vulcan. Oops. Vulcan. So Vulcan is added data address in Vulcan is 13. And we are trying to go to print secret. Secret, which is at 1340, or print, which is at 60. Right? Those are the addresses. Then how big is our buffer? So here's our buffer. Yes. Our buffer is at EVP minus hex, which is 16 hex in decimal. That's where our buffer is. So how do we exploit this? First of all, how do we exploit this without writing a script? Okay. An easy way to do this is we write a Pontool script, right? The Pontool script will read the output of this, then do the calculation to get the address to feed in that, to feed to the program. So what if we do not use Pontools? Can we do that? Let's say, without using Pontools, without writing a script, we need to overwrite this address before we know the Wolf's address. Is that possible?
Yeah, because we know the offset.
How do we use that?
When we run the program and calculate the offset.
What if we do not read the program? That's what I'm saying.
Oh.
Yeah. So this one may not be easy. Let's do that with the second one. So the idea here is, let's say, a function called waffle, right? Function called waffle, which means Valfu's stack frame, the return address should be main function's return address. Right? The main function's return address will have the same first several bytes as printf, print secret, or print flag. Does that make sense? Even though they are randomized, those are randomized, but they will be the same. So it's already there for us. So instead of overwriting the whole 4 bytes of return address, we just overwrite the last byte. Right? That should work. As long as the return address is there. But if they are not, it's possible that we also need to overwrite the second byte. Then we cannot do it because the second byte is already for the base. The second byte is not 0, okay. Which means we need to. So let's debug this to see if that works. I debug this to prove that. If this one doesn't work, I do have another program which I know that works. Okay, run it. Now let's say we disassemble main function. So main function calls valfu. So the return address on valfu's stack will be this address, which is 5655. No, 5658. D3. Okay, so that is a return address. We are trying to return to either print secret or print flag, right? So let's say where they are. Flag and print secret. Or how about print secret? Oh, print secret. So those two are at address D260 and D34D. Oh, actually, this one works. Right. We cannot return to this one. This D2 is some base here. Okay, so this D2 will be changed, and we don't know the value of it at one time. But this one, the base doesn't have this. It's 0, 0, which means for print secret, it will always be 3 bytes then 4D, and the first 3 bytes will be the same as the address first 3 bytes anyway. Okay. Now let's run that again. So now we can say these 3 bytes, these 3 here, these 3 here, they're the same. Let me just run this again to prove that. Okay, now we run it from beginning, run it again. Now I have a different address. Disassemble this, print secret, when print, let's say they're the same. Print secret is at 93. This address is also 93, same. Okay? So we just need to override 1 byte from what? 60. Should always be 60. So here is also 60. So that's how we're going to hack this. So let's say just do a easy one. Python 2. How many garbage we need? 20, right? Who said 20? Yeah,
16 for scores.
yeah, that's right, 20. 20 bytes of garbage. Then how many bytes of payload after that? Just 1 byte, 60, right? Then we just type this into the program. Oh, get a segmentation port. What's wrong here? Yeah, we're going to 40, sorry. 60 is print flag. We're going to print secret, which is 40. Here we have 9340. Here we have garbage. Not 20 bytes. Sorry, it's 20 bytes.
10 bytes of buffer.
No, that's 10 in hex. Yes. Then plus 4 bytes. So it should be 20 bytes. Then that we just have what? Oh. Where is it? Send a 0 to that? This may send a 0 to it, right? Oh. Oh, this one will send a to that. That's why. Besides 40, it will send a new line symbol there. See? And that will override the second byte. So we got a segmentation fault. Okay. So how do we get rid of that? I don't remember how to get rid of that. Anyone know Python? How do we get rid of that? Let's see. 2 result line symbol. Okay, let's revisit this later. Just
dot R. I think it's dot R strip.
Okay.
Dot R strip.
R strip.
Yep.
So that's a function.
Yeah.
R strip. Okay. Still has this. That really strips the new line
Or
here.
maybe you have to specify inside the parentheses.
Okay. Strip. Should be C. C. Still there. Yeah, well, let's revisit this later. Okay, anyway. What's to do this is we overwrite 4 bytes, right? We read the output from the program, then we write the full bytes. So here, let's say, if we use pound tools, a file, then we create a process with it. Then we're going to receive the output. Here I use the function receive until at white space because I already know what the output is. The output is val_foo is at white space the address, right? So I receive until there. Then after that, I'm trying to receive a line again and change that to an integer. And I tell that it's a hex integer. Then I get the address, which is I name it val_foo. Then the elf file's address I set as elf.address, which is val_foo's address minus elf symbols val_foo. So this one, because we use nm to see the symbol, right? So this is actually what? The offset, right? So this part is the offset. This part is the runtime address of lawful. Okay? Runtime address minus offset, what do we get? No, not text. Yes, we get the base address for maybe the whole elf. Okay, we get the base address. Then here we already set the address. So now we do a single print flag. It already have the runtime address. Okay, so that is what Home Tools does for you under the hood. So our payload is 20 bytes. Then we pack this into 4 bytes. Then that's it. Then we send the payload. Then we receive again and try to show this. So let's see if this works. And I'll put copy from slides. I need to change it a little bit. So far looks good. Oh, looks good actually. We need any indent? We don't. So it gave us a flag. Not have to go to print secret. We can also go to, we do not have to go to print flag. We can also go to print. There's no underscore. This should work as well, right? So this also gives us a flag. So this is how but this program is leaking one runtime address for us. Okay? So as long as we get one runtime address, we know everyone's runtime address. Okay, so let's say this is basically the same one. This is the same one, but what I want to show you guys is we only need to write 1 byte. So how do we write 1 byte without that new line? So maybe we can do that in Python instead of writing a program here. So here, we don't care about this. Don't care about this. Don't need this one either. Oh, hold on. Repeat. This one still give us getting more. It's two. What?
Try to use the SVR buffer. Right?
Yeah, we need that.
That will eliminate the.
So that is in my first class, like be somewhere, right? Second class. First class. Yeah, I do not use Python that much, so you can tell. Let's see this one. This. This. What's this? Maybe on the buffer. Yeah. Let's try this again. Oh, good. This one we don't have line. Perfect. So we can pipe this into the program. Still segmentation for it. What's going on? 40 or 60? Let's confirm that first. And print secret is 4D. Main function is 15, so which means that should be the same. I think it's still possible that the shell and a new line there, right? The shell may have and a new line there. Even if I do this, there was a new line sent to that. Possible. So we set a breakpoint above for basically. We run this. Okay. We're at the beginning of Volfu. We want to get this. Now we should have overwrite that. So we just exam memory from exam bytes would be enough. EBP. So we are looking at 4 bytes of save the EBP over returns or return address. Let's see what we get. Yeah, it's still add a 0 there. 4 bytes are correct. That, then there's a 1 byte, and by share and a 0 there. That's why. So we need to get rid of that. Obviously, I can write the script to get rid of that. Okay, so what do you do? So we have this, you know. So we just send. It works. Guess we don't need to pipe into that. giving us the stop there. Okay.
There's a new line in there.
Still a new line there, you think?
It looks like it.
But we do not get a segmentation fault. If it's a new line, we should get a segmentation fault. Let's see. Not giving us that. Any idea what's going on? Or can we send just one byte without sending?
Did it work when we were just sending one byte for the canary?
Canary. Oh, canary? Oh, there's no canary here.
No, but when we were doing the canary last class, we were just sending one byte at a time.
Oh, yes. Yes. We to do that, yeah. Good point. Let me take a look. You guys can also take a look, see how we can see. Oh, that one was reading from the file. So it's not directly through share. Okay, I need some time to figure out if, well, I think, oh, obviously this is possible, because I don't remember how I did it before. So this one should be the same. Just do not overwrite that. Oh, this one is different because this one takes input from command line arguments instead of std in. So because of that, so maybe we will not have that. This one. The idea is the same. Okay, you can see here, print secret is at 13, 8D, print flag is 12, main is A9, 8D. So the buffer lawful. So here we have memory copy. Buffer is at the same size, 10. Okay. But the input is from command line argument instead of let's see. It should get a segmentation fault. That's good. exactly what we want. We have 12 bytes of garbage. We have 1 byte of payload, which should have the address of 8D here. See, this one actually works. Okay. So this one works because we are sending the input as command line arguments, not std in. So share is not pending anything there. It's not pending the OA or just the 0 there. So that's why we get a flag. If we write 1 more byte, obviously we're not going to get a flag. We'll get a segmentation fault, right? Yeah, but this one works. I think the script should work. Because when we use POM tools, we don't have to send a full line. We just send. We have to send a full line. Okay, I'm not sure about that. Now I will get back to you guys later when I figure it out. Okay, so that's ASLR 2. So like I said, the problem with ASLR, first of all, this is the userland ASLR, not kernel level. Kernel level is even less frequent. Only when you reboot the system, the kernel get the 1 time of ASLR. And that happens before you compress the Linux, uncompress the Linux kernel. Right? So your Linux kernel usually is in a file called used to be ZImage, now probably different, like VM, needs something. Anyone here compiled a kernel before? Reinstalled kernel before? Okay, so that's a file. So that file is on the file system. It will be uncompressed, then load to the memory, then give the control to that to boot Linux, right? So the kernel address tray layout randomization actually happens before or at the time of compressor. When you uncompress that, you are loading the kernel to a different address, basically. Then the kernel started running there. Yeah. For user space, one idea is to make the randomization much more frequent, often. Right now, we only do that at exe when you load a file. One way to do that is we just re-randomize that at fork. Okay. So there was an NDSS paper published in 2016 to do that. So all the daemons, they're going to fork child processes, like web servers, they're going to do that. This is the same problem as the stack query, but obviously much more complicated. So now we want to add a fork, we're going to re-randomize this. But things are much more complicated here. So what kind of challenges you can think here? At load time, you randomize at once. And everything here, there are many pointers. So like you said, like you saw, there's printf. Printf has an address of a string. That's a pointer. Right? So even though that pointer, we do not know the runtime address, but we know the offset to that instruction. Then we can have a function like the PC thunk one to get a runtime address and do some calculation to get the runtime address of the string. Right? But after you run the program for a while, what kind of challenges you will face? You want to re-randomize this. Basically, all the pointers, code pointers, data pointers will have problem. If there is a data pointer, it points to some data, the code pointer, like even return address, pointing to another code address. After re-randomization, their address will be changed. So technically, you have to update all of them. Right. That's not easy. That's why I published a 13-page paper on this topic. And even this, I feel it cannot be very reliable. It would be easier if you have source code, but if you don't have source code, purely at binary level, it actually will be very challenging. So if you're interested in this, take a look at this paper. There's another paper. So this is a project we wanted to do. Then I did some search. I figured out, someone already submitted a paper. So this is to do a re-randomization or randomization for microcontrollers. Like I said, they do not have MMUs. Okay. We want to re-randomize them after some time it is running. We still need to address the challenges the first paper addressed, but we can directly use that approach. The main problem here is how do you even randomize code here? You don't have MMU. The code is in flash fixed address. Obviously, you take it out from flash and write to flash, that'll be very slow or even may not be working. Okay. So you do not really execute code on flash. You copy the code from flash to DRAM, then randomize on DRAM. That's a basic idea. So this is probably the first work of ASLR for microcontroller-based systems. Okay, so next defense we will talk about is Secure Computation Module, or Seccomp. The name is big, but it doesn't cover that many things. Linux has many different security features. One of the very famous one is called the Loadable Security Module. That one can be hooked at any place at kernel, so that is big. So this one is not that big. This is basically a system call firewall. And this has been embedded in modern Linux kernel. Take some kind of a policy in the form of rules. And those rules will let you allow system calls, disallow system calls, or filter, allow or disallow based on argument. So this is a firewall. Okay, what is the action here? What is the data you're trying to send to the kernel? Okay. This is a firewall between user space and parent. System call is an interface. Right? And those rules are inherited by the children process. A little bit of history, started in 2005, also merged into the kernel in 2005. Android also uses this right now. It's actually very simple. To demonstrate that. Some macro here. I'm going to compile this into two different programs. One with the 4 lines of code in the macro, another one without. Without that, we basically just have two things. We just have execve, then return. And in that execve, we are going to execute cat, and the parameter is just a flag. That's it. So it will count the flag for us. That we're going to set up the firewall. First, we set up the secure module context. Then we will say we initialize the policy as all system calls are allowed. Then we add saying that if there is a execve system call, we are going to kill this process. Then we just load that policy. That's it. So All this, you will just give us the flag. If we version, we disallow this. You will just give us bad system call. Okay. So you have a firewall. So you can set up the firewall when the program runs. Then even if there is a bug in your program, and the attackers can inject the shellcode or use return to libc, eventually they have to execute execve, then the firewall will be blocking that. Okay. But attackers can also bypass this. For example, what other approaches you can think without using execve, but you can still get a flag? You can use open send file, right? Two system calls. Okay. We can also block that. What other approaches we can use? What other system calls we can do? We do not open send file. We do not open read, right? We do not do execve. Okay, let's see who can come up with a one system call approach. Okay, and you are going to use this next week. This is very important next week. Because next week you are going to develop 8 and 6 bytes shellcode, very small, okay? And you need that as a system call.
Forking, also called.
Forking is a different system call.
Itself and run that, would that work or?
No, because after you fork, the new program will have the same firewall. The child process will have the same firewall. We talked about this last semester actually. So Linux actually separate fork and exe, those two system calls intentionally. Okay. The reason is between that we can do file description, file redirections. Yeah. Windows doesn't do that. Windows, they only have a interface called create process. That's basically fork and execve at the same time. Okay, any idea? So the flag is a file on the file system, right? Okay. It's a C library function. Yeah. System eventually calls execve. Yeah. So when you have a file in a file system, you have root privilege, want to read it, right? You want to hack it directly, what you can do. Let's say you do not directly read it, you read it later, but what you can do is a root privilege. Copy root ID.
Copy or they remove the file somehow.
Okay. You are getting close. Copy or move, it doesn't really change the permission. You still have the same permission. Yeah. But you are getting there, very close. Because you are root, you can copy and move them. But it doesn't change the permission.
Something like
That's just one system call, right? That is a flag file in the file system. You make one system call, change the mode of that. Then that file can be accessed by everyone. Yes. Let's see. That's actually all I have for today. You guys can stay here for the homework, or if you want to leave early, that's okay too. Yeah. So next 2 weeks, we were working on shellcode workshop. We have many challenges there that you are going to develop one by one, from self-changing shellcode. The shellcode must change itself, to super short shellcode, like 6 bytes, 4 bytes, something like that. Yeah. And we will start with a baseline. And the baseline, we're going to start with the change mode one, because it's much simpler than what we already have. What we have right now is like 21 bytes, I believe. Yeah. Starting from 21 bytes to 6 bytes, that's almost impossible. So we're going to that change mode one. I believe that one will be 15, 16 bytes, just like that. Then we change that smaller, eventually to 6 bytes. Thank you. Thank you, guys.